The image is deceptive. A convoy of steel trailers white with frost winds slowly across a tundra road near Murmansk. Inside each one, reindeer, alive, alert, moving with the sway of the vehicle. They look adapted to this world of ice. But what their thick fur conceals is a fragility hidden in biology, a sensitivity not to cold but to change. The paradox begins here. These animals survive temperatures that would kill most livestock in minutes, yet they can collapse under a single, abrupt shift in ambient temperature. Their bodies are tundra-calibrated, stable under extremes, but unstable under transition. That's why moving reindeer is not about keeping them cold. It's about controlling the moment between climates. The thermal inertia systems designed for them borrow logic from Arctic naval fleets. Ships that cross frozen oceans without letting their hulls contract too fast to avoid metal fractures. In livestock logistics, this becomes a strategy of maintaining ambient buffer zones, creating what engineers call temperature tunnels around the animals, zones where heat change is slow, stable, and survivable. But thermal stability is only one part of the equation. The second is movement itself. Unlike industrial livestock bred for confinement, reindeer are semi-wild. They come from open ranges, not feedlots. Their neurophysiology responds to confinement with sensory overload. Vibration, humidity, CO2 accumulation, even the acoustics of metal walls trigger survival instincts that spike their cortisol levels. And here, agricultural engineering steps in not just as transport but as translation. Transport trailers must behave like controlled ecosystems, finely tuned to a biology that evolved in stillness. Airflow systems mirror those in poultry climate control modules, but recalibrated for cervids. Floors must absorb impact the way a forest floor does, soft, uneven, and non-repetitive. Every mechanical decision must anticipate how the animal perceives the journey, not just how it survives it. This is where ancient logistics meet modern design. During World War II, Arctic naval convoys crossing the Barents Sea developed precise thermal flow simulations to prevent systems from freezing, not because the ambient temperature was too low, but because a sudden drop could crack valves, weaken turbines, and paralyze steel. That logic survives today inside the reindeer caravans crossing the Siberian steppe. Controlled ventilation boxcars, outfitted with shock-damping floors and humidity-tuned enclosures, replicate that same concept. Keep the environment stable, not just cold. Preserve function, not just form. There's another dimension to this transport system, one few outside the region even know exists. From the Arctic Circle through Mongolia and into northern China, runs a live animal corridor moving over 3 million head per year. Reindeer, yaks, sheep, and even semi-domesticated moose are driven through it, passing across at least 4 distinct climate zones in a matter of days. And here lies the final tension. Logistical systems designed for homogeneous conditions, flat roads, stable temperatures, consistent terrain, are now pushed into environments that shift every 100 kilometers. Frost gives way to dry wind, hills flatten into plains, altitude drops, humidity rises, yet the systems must hold. The animals must stay alive. The environment, it turns out, is not the enemy. It's the change in environment that breaks the chain. That's the heart of reindeer logistics. Not the spectacle of trucks in snow, but the invisible, calculated effort to mimic a world these animals already understand. Not with diesel, not with steel, but with strategy, with insulation, vibration damping, smart ventilation, and an understanding of biology so precise it might as well be choreography. Moving these animals is not a cold chain operation. It's a biomechanical ballet, performed across frozen frontiers. They don't scream, they don't thrash. But reindeer under stress release a silent alarm, one measured not in sound, but in blood chemistry. During long-distance transport, even when external conditions seem ideal, something invisible can undermine the entire operation. Vibration, the kind generated by a truck's chassis, by tires crossing uneven terrain, by the subtle, constant tremor of metal over asphalt. Over time, these micro-vibrations cause a cascade inside the animal's body. Cortisol surges, muscle fibers break down, immune systems weaken, meat quality degrades, and none of it is visible until it's too late. This is the biological cost of movement without modulation. The solution begins underneath the hooves. New transport units use pneumatic suspension systems, but more importantly, integrate what engineers call adaptive gait platforms. These platforms are pressure-sensitive surfaces installed on the floor of each unit. They detect the animal's natural weight distribution patterns in real time and adjust the frequency of vibration damping accordingly. The effect is subtle but transformative. Instead of riding on a fixed, trembling base, the reindeer move with the platform, like walking across soft tundra, not vibrating steel. It's a mechanical empathy. The system listens and responds, not just operates. A study conducted in northern Finland brought this theory into sharp focus. 2 convoys, identical routes, identical reindeer, one with damping floors, one without. The results: stress hormone levels dropped by 37% in the modified convoy. Not only did injuries decrease, but post-transport recovery improved. Animals were more alert. Respiratory rhythms returned to baseline faster. And when later assessed for meat yield, the difference in muscle integrity was measurable. What looked like a simple floor adjustment became a full-bodied intervention. This isn't abstract science. One logistics team in Norway faced the real-world cost of skipping this layer of design. Their reindeer convoy reached the border on time, but veterinary inspectors found signs of immunosuppression in the animals. Blood tests confirmed elevated cortisol and white cell irregularities. The result: a full quarantine, weeks of delay, financial loss, and all of it traced back to one overlooked variable: harmonic frequencies generated by tires at cruising speed. The rhythm of the wheels had matched a stress trigger in the animal's neuromuscular systems. A small mismatch of biology and mechanics turned into a systemic failure. So here, the metaphor becomes unavoidable. Transporting live reindeer without vibration mitigation is like harvesting grapes with a hammer. The form might survive, the skin might remain intact, but inside, the structure is collapsing. The integrity is compromised. The damage is already done. And in high-scale logistics where quality is everything and error is expensive, that's not a risk. That's a design flaw waiting to happen. Inside a sealed livestock trailer, cold air often gives the illusion of freshness. There's frost on the floor, condensation on the walls. To the eye, the environment seems pristine, harsh, but breathable. Yet beneath the surface, the chemistry tells a different story. In confined transport, reindeer metabolize fast. Their basal metabolic rate is high, especially under stress. That means more CO2, more heat, more ethylene compounds released through respiration, all within a sealed volume that rarely behaves as engineers assume it will. The critical flaw isn't the cold, it's the belief that cold is enough. Many winter transport operations still rely on fixed-rate fan systems or passive airflow designs. These work well in temperature-controlled warehouses or short-haul routes. But inside a moving reindeer unit, those assumptions break down. Within just a few hours, CO2 begins to accumulate near the floor, where the animals breathe. Ethylene concentration rises, and with every additional kilometer, their ability to tolerate confinement drops. What begins as mild fatigue escalates into hypoxia, behavior suppression, and, in worst cases, transport mortality. To solve this, a new class of hybrid ventilation systems has emerged. These aren't simply stronger fans. They are intelligent air management networks, designed to shift modes based on live environmental data. At rest, they operate on passive air induction, minimizing noise and preserving thermal stability. But once CO2 or ethylene levels cross a calibrated threshold, typically detected by sensors placed near the animal's lower lung zone, the system shifts. Dynamic cross-vent jets activate, pulling fresh air through pressure-controlled ducts while maintaining temperature uniformity. It's not just airflow. It's microclimate engineering, executed in motion. Field data confirms the urgency. According to livestock transport audits published by the Food and Agriculture Organization, 1 in 4 reindeer shipments across Eurasia shows CO2 levels exceeding safety thresholds after just 6 hours on the road. The primary cause? Improper fan cycling rates and static ventilation assumptions. In cold environments, operators often reduce air turnover to preserve heat. But this sacrifices air composition, turning a thermally safe space into a chemically unstable one. A logistics company in Kazakhstan found a solution in adaptation, not intensity. By shifting from fixed-speed systems to pressure-regulated and temperature-compensated air units, they doubled the viable export time for live reindeer. Their trailers now respond dynamically to atmospheric feedback, modulating airflow, humidity, and gas concentration based on location, altitude, and animal behavior. The result isn't just extended transport range. It's increased survival, reduced stress, and improved product value. Designing air for livestock isn't about brute force. It's about rhythm, about listening to how animals breathe under pressure and how gas dynamics behave inside metal enclosures over long distances. In that sense, the principle mirrors something deeply familiar to those in crop sciences: a greenhouse. In a greenhouse, survival depends on the subtle modulation of air, heat, and gas. Not all at once, but precisely when and where it's needed. The same applies to reindeer transport. Air must move like a system with intelligence, zoned, dynamic, responsive. Otherwise, the journey becomes a chemical trap, and one that no amount of cold can fix. There is a silent error embedded in how modern logistics often approaches the movement of living beings. The language of transport, units and loads and shipments, flattens the complexity of life into cargo metrics. But reindeer resist that reduction. They are not livestock in the traditional sense, bred for confinement and conditioned to human-managed rhythms. They are semi-wild migratory animals, cervids evolved for constant adaptation across landscapes where temperature, wind, light, and sound shift hour by hour. To treat them as static freight is not just biologically naive, it's mechanically inefficient. Cold for reindeer is not an enemy, but cold without transition management becomes a risk. Unlike perishable goods that require uniform low temperatures to preserve integrity, reindeer require thermal constancy, not thermal extremity. Their internal systems are highly tolerant to cold yet fragile in the face of abrupt thermal gradients. Applying cold chain thinking, designed for inanimate food products, to a biologically active heat-regulating organism, creates contradiction. The result is not stability, but stress. This is why the best reindeer transport systems are no longer modeled on refrigeration. They are modeled on agroecological mimicry. One of the most significant breakthroughs came when engineers began applying knowledge from soil compaction mechanics to trailer floor design. Just as modern forage harvesters adjust blade height and downforce depending on terrain softness or resistance, reindeer transport units now use flexible base layering. These floors incorporate pressure-distributing mats, dynamic dampers, and segmented support structures that respond to how animals shift weight during transport. Instead of forcing the reindeer to conform to rigid geometry, the surface adapts, absorbing microshocks and maintaining joint alignment. The system doesn't dominate the animal's posture, it harmonizes with it. This mechanical sensitivity extends to the walls themselves. In a joint venture between Swedish animal biologists and Japanese materials engineers, modular soft wall containers were developed to mimic the quiet, diffused light of natural habitats. These containers integrate zoned lighting, noise-dampening insulation, and internal ventilation nodes controlled by GPS triggers. When a convoy descends from Siberian plateau into Mongolian plains, the environmental conditions inside the trailer adjust without delay. Air turnover increases to accommodate rising humidity. Acoustic absorption adapts to compensate for denser external noise. Even CO2 extraction rates shift, guided by sensor input calibrated not to arbitrary thresholds, but to servid ethology, the behavioral science of how these animals manage stress. This shift in logic, from freight to habitat, from temperature to rhythm, marks the frontier of intelligent livestock transport. It reveals a new kind of efficiency, not one based on brute force, but on biomechanical dialogue. The machine speaks with the animal, through vibration, airflow, and surface tension, and the outcome is not just survival, but stability, behavioral, metabolic, and structural, because reindeer cannot be moved the way crates are moved. Their transport is not a matter of insulation, but synchronization. You don't guide 11 million of them across the globe by force. You do it by creating a mobile tundra, where every sensor, every panel, every floor section understands its role in a larger biological choreography. It's not a supply chain, it's an engineered migration, and that distinction changes everything, not just for the animals, but for the future of logistics itself.